Okay, so we are now in chapter 7. Chapter 7 is on differential equations. Okay, differential equations. Chapter 7 touches upon it. It gives kind of a nice overview of differential equations, but differential equations is a field with a lot of material, and we have a separate course at Montgomery College called, as you know, Math 282, differential equations. And some of you said you need to take that course, and I really recommend, I think really everybody should take it, to be honest, but I'll leave that up to you. At any rate, what is a differential equation? Well, this is what we're going to talk about, section 7.1, where we model with differential equations. Let me give you a moment to copy this example down, and then we'll discuss the example. Okay, so let's see here. A differential equation. Differential equations. So let me just see now. They've sort of changed the top here. What I mean is I'm trying to. Okay, I'll pick that. Pick blue. Okay, there we go. All right. So a differential equation. Let me just see here. One moment. Forgive me, class. I'm just trying to. There's some features or something here on my viewer that I'm trying to. Okay, good. It went away. Good. All right. Must be an update or something. Okay. So what is a differential equation? What is a differential equation? Well, this here is a differential equation. 2y double prime plus y prime minus y equals 0. Okay, that is a differential equation. Now, if we look at that, we could also express that differential equation like this. Hold on here, class. I have to get accustomed to this thing here. One moment. Just give me a moment. Okay, so we could think of this as 2 times the second derivative of y with respect to x plus the derivative of y with respect to x minus y equals 0. And it's called a differential equation because it has derivatives in it. Okay, a differential equation is an equation that has derivatives in it. And when we model phenomena in science and math and engineering, when we have applications we want to model these different types of phenomena that occur. Like, for instance, an example would be if you have a mass attached to a spring, and you release the mass, and the mass, maybe it's on like a table, and let's suppose there's no friction. I mean, theoretically, that's difficult, right? But you know, you release the mass, and the mass goes back and forth because it's attached to the spring, and the spring goes back and forth. It expands, contracts, expands, contracts. The position of the mass relative to time can be modeled with what's called a second order differential equation. And what we have here is a second order differential equation. Okay, because hold on here. The highest derivative, okay, the highest derivative is of second degree. Okay, a second order derivative. How many remember like orders of derivative? Like y prime is first order derivative, y double prime is second order derivative, y triple prime is third order derivative. How many maybe remember that from Calculus 1? Okay, good. Ange and Kaj remember that. Well, what we have here is a second order differential equation. And what's being asked here is, well, of course, if we have, just like any equation, we're always interested in solving the equation. So how do we solve this second order differential equation? Well, you don't know how to solve it yet. You haven't learned how to do that. But what they're saying here, what they're saying in this problem, okay, is they're saying, well, hold on here. They're saying that y equals e to the power rx is a solution to the differential equation. They're saying that there is a function, an exponential function, that will be a solution to this differential equation here. But this solution, e to the rx power, is not useful to us yet because we need to figure out what the r values are. Okay, so when they say for what values does this exponential function satisfy the differential equation, of course they mean for what r values. So, okay, well, so let's take an analogy here. Let's take an analogy. Okay, sorry, let me get used to this new, there's a new writing tool here in Blackboard, at least for today, and I'm getting used to it here. So, okay. If I had an equation 2x plus 1 equals 7. Okay, what's the solution to 2x plus 1 equals 7? What's the solution to that equation? Okay, 3, that's right. And how do we know that? How do we know that? Let's say that we don't know how to solve this very basic equation, but yet you say, Dr. Judy, x equals 3 is the solution. How can we do that? Well, so Ange, we could solve for x. We could solve the equation, okay, by subtracting 1 on both sides and all that. We could solve the equation algebraically, but what I'm trying to do here is make an analogy. We have a differential equation here that we don't know how to solve, and you're being told that e to the rx is a solution to the differential equation. So if analogously for 2x plus 1 equals 7, if you're told x equals 3 is the solution, and let's say you didn't know how to solve that basic equation, how would you verify that x equals 3 is indeed a solution to 2x plus 1 equals 7? How would you verify that? What would you do? That's right. That's right, Ants. That's right, Mario. You plug in 3. So 2 times 3 plus 1 does equal 7. So x equals 3 is a solution. So you see, we didn't know how to solve. We didn't have to know how to solve this algebraic equation 2x plus 1 equals 7. We didn't have to know how to solve that to be able to verify that x equals 3 is a solution, because we can substitute x equals 3 in the equation and see that 2 times 3 plus 1 equals 7. Well, similarly, what we're going to do is, since we're told that this y equals e to the rx, that exponential function, we're told it satisfies this differential equation, we're going to substitute it in. And then we'll be able to figure out what r is. Okay, so this exercise is designed to get you used to seeing a differential equation and playing around with it a little bit. So let's go to the solution. Here we are. Okay, so if of course here's the differential equation. Okay, here's that differential equation. And in order for me to like if y equals e to the rx power, okay, well, I can substitute that in for the y here. But then, in order to substitute in the derivative of y and the second derivative of y, I need to find those derivatives. So if y equals e to the rx power, then y prime would equal r times e to the rx power. And then the second derivative of y would be r squared times e to the rx power. And now I can substitute in the first and second derivative. I can substitute those in the differential equation, and that's going to give me this then, this equation here, 2r squared times e to the rx power, 2r squared times e to the rx power plus r times e to the rx power minus x. Are there any questions, up to here? Okay, all right. Well, so our goal is we want to solve for r. We want to solve for r so that we know what specific exponential function is a solution to the differential equation. So I have to know what that unknown constant r is. Well, look at what we can do here. We have 3 terms here, all of which have e to the rx power as in them. So why don't I factor out e to the rx power? And that's going to give me then e to the rx power times the quantity 2r squared plus r minus 1, and we set that equal to 0. Okay. All right, now I'm going to, since we're here, let me just see here. Let me just play a little bit with this normal. Okay, this is fine. We'll go with normal font. That's fine. One moment. Sorry. Okay, so this implies, so like if you had a times b equals 0, what does that imply when a times, so this is like a little bit of an aside here, but if you had a times b equals 0, what does that imply? What has to be true if a times b equals 0? That means a would equal, that's right, Taj. That's right, Nathaniel. Either A equals 0 or B equals 0, one or the other. So similarly, we have a product here of two functions. Product of two functions being equal to 0. So this means either e to the rx power equals 0 or 2r squared plus r minus 1 equals 0. Right? It's one or the other. But notice if we look, sorry, hold on, still getting used to this new format here. One moment. Yeah, if we look at this equation, e to the rx equals 0, does that have a solution? Does that have a solution at all? I mean, if we think about, that's right, it doesn't. It doesn't. Nathaniel's right on that. D'Angelo's right. There's no solution on that. Okay, no solution. So like for instance, if I were to if I were to, you know, I have an x-axis and a y-axis, and if I were to here, I'm just getting used to this new thing here. If I were to draw, you know, different exponential functions, okay, this would be exponential increase. This exponential function would be the exponential decay. But you see, the exponential functions never go below. I mean, like you know, this is again e to the rx power for different values of r. This would be when r is hold on here, this thing off. This function here would be when r is less than 0. And this function here would be when r is greater than 0. So, you know, you have exponential decay and exponential growth. How many recall that from pre-calculus? How the value of r here determines whether you have an increasing function or a decreasing function. Yeah, and so I mean, that's right. Thank you, Ansh. Thank you, Taj. So, but for any exponential function, it will never take on the value of 0. So this particular equation has no solution. So that means then that the solutions to r have to come from this equation. And that's why we only have this equation here, this quadratic equation. Well, not quadratic equation. It's a second order equation. Yeah, it's a quadratic equation. That's right. That's right. But do we need to use quadratic formula? Not necessarily. It turns out we can factor that quadratic equation into factors 2r minus 1 and r plus 1. Okay, so that means then that we set each of them, if 2r minus 1 times r plus 1 equals 0, then either 2r minus 1 equals 0 or r plus 1 equals 0. And so you get r equals a half or r equals -1. And so there are two possible solutions. Ange, you said we can see r equals -1. Yeah, well, I mean, you have, that's one of the possible values for r. Right, and then the other possible value for r is r equals a half. So this second order differential equation, it turns out, has two solutions. Okay, two solutions. And so we've solved the problem. And it's a nice little problem because it kind of forces you to really understand, you know, what a differential equation is, what it, in a sense, what it, you know, what does it mean when you see those derivatives and so forth. Well, yeah, differential equation is an equation with derivatives, and this example really reinforces that. All right, are there any questions on that problem at all? So, all right. So it's interesting, right, that you have two solutions. If you had a third order differential equation where you had a third derivative in the equation, how many solutions do you think you would get? Well, don't worry about that for now, okay? Let's go to the next example. Let's keep it simple. Let's keep it simple. Okay, here's another example. Let me give you a moment to copy this example down, and we'll go over the solution. Okay. So this example is an example. It's like in the book. This example is not one of the examples in the book. It's an additional one that I'm doing. To add a little variety to your examples that you have. All right, let me give you a moment to copy that example down. Okay, so let's take a look at this problem. So differential equations, we use them to model different kinds of situations that arise in science. And they are seen in all fields of science. Um, you know, engineering, physics, biology, um, uh, you know, economics. Uh, they are just, you know, they are widespread because we can model different situations in math, science, and all the fields. We can model situations with differential equations. And in this example here, what we have is we're going to model a population. We're going to model a population with a differential equation. So dp dt, okay, dp dt is a rate, right? It's a growth rate, right? So how does the population change with respect to time? Okay, what's the growth rate? And the growth rate is equal, in this, for this little example, it equals 1.2 times the population minus 1.2 times the square of the population over 4,200. Okay, and we have some very fundamental questions here. First of all, for what values of the population, for what values of P is the population increasing? Okay, so if the population reaches, well, I want to be a little careful how I phrase it, but do you think a population, like take deer, take like the deer in Montgomery County, okay? There was one in the middle of the road last night when I was driving back from somewhere a little late, and one right like in the middle of the road, you know, in the divider there. So got to watch out for them. But do you think that the deer population would grow always based on the population? Can the deer population continually grow and grow and grow and grow in Montgomery County? Mario doesn't think so. Okay, why not, Mario? Why not? What might affect the growth of the population? Okay, Mario says there's a maximum capacity, which we would call a carrying capacity. The carrying capacity is the normal term we use for that. Very good, Mario. And well, why why couldn't the population just keep growing and growing and growing? What's going to limit the growth rate? What's going to limit the growth of the population of deer? That's right. Good. That's right, Mario. Food and space. Okay, so if you had, so like, if you think about it, if your population of deer is small, okay, there's room for the population to grow, right? Because there are food sources available and space. You know, the deer need space. They can't, if they need space, you know, they have their, I'm not a deer expert, but I assume, you know, they have their territories and so forth. And, you know, there's only so much space for the deer to comfortably live. Okay, when there's too many deer, don't you notice we often like, well, how many have heard of like, well, I don't want to get too trying to think just kind of carefully how I phrase it, but you know, what happens when the deer population grows too big? What do counties tend to do? Well, this is actually, yeah, they hunt. They hunt. That's right, Joseph, Mario, and Ange. They hunt. So really, this is really I'm making it a little more complicated than I need to for our class. When you get into differential equations, you'll deal with hunting or harvesting of a population. But I mean, the point is the deer, when they grow too much, it gets unsafe because they're on the roads, there are accidents, so they got to keep the population at bay. But in this situation, I mean, even if we just ignore that, we know that the deer population can't grow forever, no matter what, because they're going to run out of food, right? They're going to run out of food. That's the number one thing. So at some point, the deer population isn't going to grow anymore. And if the population is like too much for the space, the deer population could decrease. Okay. And then you have situations where maybe the deer population stays constant. That's what's called equilibrium, when the deer population stays level. In other words, it doesn't grow, deer population doesn't grow, and it doesn't go down. That's called equilibrium. And you see, a biologist, based on data, can find a differential equation to model deer population in a certain region. And let's just suppose this is our differential equation. Well, remember how are we going to answer these questions? How are we going to answer these questions? Well, when you talked about increasing and decreasing, remember in Calculus 1 when you had functions and you wanted to know where the functions were increasing and decreasing? Okay, how many recall that what you would try to do is you would take the function and factor it to help you see where the function increases, decreases, where it's concave up, concave down, that sort of thing? How many recall that from Calculus 1? Yeah, Ange recalls it. Does anybody else? I hope somebody else recalls that. Okay, Taj recalls it. And so you see, what we can do here is we can take note of something. Okay, and I'm trying to be sort of conversational about this, and let me know if you have any questions. But you see here on the right-hand side, we can do a little factoring here. So what we're going to do is we're going to factor the right-hand side of this differential equation. Okay, so let's go to the next page. Here's the next page. And what I've done is I factored out a common factor of 1.2p. And so now my differential equation, now dp dt, can be written as the product of 1.2p times the other factor 1 minus p over 4,200. Okay, it's the product of those two factors. Okay, so this is dp dt. When the differential equation, when it is written out in factored form, we can learn a lot. So like for instance, the first question asks, when is the population decreasing? And by the way, the differential equation here, you notice the differential equation that is not P, I want to say this the right way. One moment. So sorry, give me one moment here. So P is understood to be a function of time. Okay, the population changes with respect to time. But in the differential equation, they don't write P of t. They just write P, but it's understood to be a function of time. And in this differential equation here, there's no like t value that shows separately. So this is what's called, this differential equation here is called an autonomous differential equation, because the derivative is a function of the population. Now the population is in turn a function of time, but the derivative dp dt can be thought of directly as a function of the population. So the t is not in essence involved. Well, I want to say it the right way. The variable t is not, I mean, as t changes, p changes, but we can look at the differential equation, we can study it based on our knowledge of the population alone, okay? Independent of time, so to speak, even though population does change with respect to time. So, okay, well, now, first question was, when does the population increase? Okay, well, so when dp dt is greater than 0, okay, when dp dt is greater than 0, okay, this means the population p increases with respect to time. And dp dt, based on the differential equation above, you know, based on our differential equation above here, let me just circle it. I have to, one moment. The derivative here is, again, the product of these two factors, 1.2 times p and 1 minus p over 4,200. Now, 1.2 times p, that factor is always positive, right? That factor is always positive, because how can you have a negative population, right? So whether the derivative is positive or negative depends on the sign of this second factor, 1 minus p over 4,200. Well, if p is between, if p there is between 0 and 4,200, that's going to make that second factor be positive, okay? Because, you know, if you think about 1 minus p over 4,200, when is it positive? It would be positive when, just trying to show a few details here. It would be positive, okay, when 1 is greater than p over 4,200, or when p is less than 4,200. So I can multiply both sides here by 4,200, right? And I end up getting p is less than 4,200. And so there you go. When p is between 0 and 4,200, the derivative is positive. So that means the population increases when the population value is between 0 and 4,200. On the other hand, the derivative will be negative. The derivative will be negative, okay, if the population is greater than 4,200, because that would make this second factor negative. 1 minus p over 4,200 would be negative when p is greater than 4,200. So that means when the population gets too big, you know, above 4,200, the area can't sustain that growth. Okay, so 4,200, well, what is 4,200? What is 4,200? Well, 4,200 is what's called a carrying capacity. The differential equation would equal 0 for P equals 0 or P equals 4,200. Those are what are called equilibrium solutions. And when we say the derivative equals 0, that means the population stays constant with time t. If the derivative equals 0, okay, then the population stays constant. Okay? Because the derivative of a constant is equal to 0. And a constant function is a horizontal function. Please let me know if you have any questions on A, B, or C here. Please let me know. Who's feeling good so far? Maybe give me a thumbs up if you're feeling okay so far. Okay, Ange is good. Mario's good, and Jan, and Nathaniel. Very good. Excellent, excellent. Okay, so these are very important when we study differential equations, and I can actually draw you a picture of like we don't know. I mean, what we're doing here is we're analyzing for what values of the population would the population grow, would the population decrease, or the population be constant. But notice we still don't know a formula for the population. We don't have a formula. But it's okay, because the fact that we know the differential equation allows us to qualitatively study this population function P of t, even though we don't know the formula. And in fact, I can even graph the population function for different initial values of the population. So on the next page here, if we're good, I'll go to the next page. All right. So here, what I have is a graph of just the population function. So this is P of t. So like, let's say initially your population is, hold on, I don't know why it's doing that. Hold on, let me get this off. Hold on. Let me try that again. I'm telling you, you think you learn, you think you know everything, and I mean, nobody knows everything, but you know, I always get surprises here. All right, so if your initial population, of say deer were 6,000, okay, 6,000 deer, then the population decreases to 4,200, and that's because we were told that if the population were greater than 4,200, this is the part, you know, in part B there, if the population is greater than 4,200, then the derivative dp dt, and notice now the y-axis, is well, the x-axis is t, and the, hold on here, I got to get this thing off here, and the you have to forgive me, I'm trying to navigate this new system here. All right, so you see the vertical axis is P, is a P, and the horizontal axis is T. So we learned, let me just go back to the thing here. we learned that if the initial value of the population is greater than 4,200, population has to decrease. And we learned also that if the population initial value, if it's between 0 and 4,200, which 1,000 is, then the population has to increase. And it increases up to the carrying capacity of 4,200. And then we learned that if the population were at 0, well, it's going to stay 0. That's an equilibrium solution. And if the population of deer were at 4,200, the population would remain constant. And you wouldn't need, I mean, basically that's sort of ideal, right? If the populations level off at a constant and we can live with that, then that's nice, right? Okay, are there any questions on that? You might remember from your I'm just writing down that differential equation again. You might remember from your pre-calculus days exponential growth. And you see, if we focus on this part of the differential equation, when p is small, this factor here, the second factor, is going to be small. Okay, and it's going to be close to 1. So for small values of p, the differential equation when p is small, this is for small values of p now, small values of p. The differential equation is approximately going to be equal to 1.2 times p. Okay, now, but as p gets larger, then this second factor is going to be more and more important. So what I'm trying to say here is if you look at how this graph is, for if the initial population is 1,000 and the population decreases, the way the population would increase is like this. Initially, it's going to be like concave up growth, okay, like exponential growth. But then the growth will level off and go concave down as you get towards the carrying capacity, which makes perfect sense, right? I mean, would it make sense to say that the deer population grows like this? Hold on. I mean, would that make sense to say the deer population grows linearly up to the carrying capacity? Would that make sense? No, it would not. It would not make sense. That's not how nature is, right? For animals and stuff. Okay, so this wouldn't make sense. Now this particular growth curve is it's what's called a logistic growth, a logistic model, and there is a formula that you can find to model the that growth curve. But again, we're in section 7.1, so we're not ready to get into that yet. Certainly in differential equations, Math 282, you will see that. But right now we're just, we're in 182 and we're just learning the basics. Are there any questions at all about this problem? I want to do one more before we go on break. Are there any questions? Okay, how many think so far this is pretty cool, seeing this application here of a differential equation to model population growth? How many are like, hey, this is kind of cool? I'm curious. Okay, Mario and Ange are liking it. All right. Taj likes it. Ethan, what do you think? Do you like it too? All right. Well, David, what do you think? Jinxon likes it. So I'm just calling out a few names here. Okay. Ethan likes it. Good. All right. Well, good, good, good. Wonderful, wonderful. Well, let's go to another example. Let's do one more here. Let me give you a moment to copy this example down, okay? All right. Okay, so, all right. In this problem, we have this differential equation, x squared times y prime plus x times y equals 1. That's our differential equation. And we're being told that y equals the log of x plus c divided by x. We're being told that that is a solution to this differential equation. And you notice there's a constant c here. So just like constant of integration, that constant c is a general constant. So what this is saying is that a differential equation, since that constant c can be any constant, any real constant, there's an infinite number of solutions to this differential equation. This is what's called, this is a general A general solution. Okay, we call that a general solution. Now, the thing is, okay, if we add a condition, if we put in a condition, for instance, that y of 2 equals 1, this means when x equals 2, y equals 1. Okay, when we put in this initial condition, okay, we're solving what we call an initial value problem. And when you put in that initial condition, then you're going to find a specific value for that constant c. Okay, you're going to find a specific value for that constant c. So let's go ahead here and let's show that every member of this family of solutions, family of functions, is a solution to the differential equation. How are we going to do that? We're going to plug that function in the differential equation and see if it satisfies the differential equation. So let me go to the next page then, if we're good. Are there any questions so far? Okay. Okay, so of course, the differential equation, right? I don't know why that's showing. Get that off, please. Thank you. I mean, our differential equation is x squared times y prime plus xy equals 1. So what we're going to do is we're going to substitute in our function in the left side of the differential equation and work it out and see if we get a 1. Well, the left side of the differential equation involves naturally a y prime, a derivative. So I have to find the derivative of this function y. And since this function y, which is the log of x plus c divided by x, since that's a quotient, we have to use the quotient rule, right? This is the quotient rule for finding a derivative. And we do that. We do that here. And when I simplify it, I find out that the derivative of y is equal to 1 minus the log of x minus a constant divided by x squared. Now we're all prepared. We're all prepared to substitute in. We're all prepared to substitute in. Hold on here. We're all prepared to substitute in y prime, and we're all prepared to substitute in y, which we do. Now, it turns out, again, we want this, we want to know if this equals 1. It has to equal 1 if this is going to be a solution to the differential equation. Well, the x's simplify out there. Okay, the x's simplify out there. And we're left with 1 minus the log of, I'm sorry, and the x squareds also simplify out, right? And so you're left with 1 minus the log of x minus c plus log of x plus c. And look at this. Look at this. A lot of things cancel out here. A lot of things cancel out. One moment. The logs go out, the constants go out, and you're equal to 1, and you get a 1. So that checked out. That checked out. Okay, that checked out. Okay, so let me clear the annotations here. I want to make sure, you know. So therefore, we have a family of solutions to the DE. What does DE stand for? That's an abbreviation, DE. That's right, differential equation. That's right, Tosh. Okay, and so that's our general solution. That we've confirmed, we verified that that solution is a solution to the differential equation. Now, how did they come up with that solution? Well, you might have to take differential equations, 280, Math 282, to see that. Okay. We are going to learn a technique called separation of variables that'll help us solve some differential equations. This one here, we would need another technique, but for this differential equation, but that's fine. That's fine. Are there any questions? All right, well, for this family of solutions, now, let's say we have a family of solutions. We have this family of solutions, and we want the solution that's going to satisfy the initial condition that when x equals 2, y equals 1. Well, all we have to do then to find that solution, okay, is just substitute in, and let me use the little marker here. Yeah, I mean, when x equals 2, y equals 1. So there's y equals 1 when x equals 2. Hold on, though. I want to actually go up a little bit. Right, right. Oh, yeah, yeah. So, we're putting an x in everywhere. We see an x. So here also, x equals 2. So you see, in that family, the family was right. The family of solutions is y equals log of x plus c all divided by x. And so since when x equals 2, y equals 1, I just substitute in. I substitute in for where I see the x, I put in x equals 2. Where I see the y, I put in y equals 1, like I did over here. and then I can solve for the constant. And the constant, it turns out, is going to be 2 minus the log of 2. And so the solution now to what we call the initial value problem, okay, this is an initial value problem here, because in addition to the differential equation, we also have an initial condition. So there, then, we get a very, well, we get a specific solution, and it's a unique solution. If we had a different initial condition, we would get a different unique solution. And this is assuming that the differential equation is it's a well-behaved differential equation. We don't need to get into that you'll learn more about that in Math 282. But generally, for well-behaved differential equations, which you're going to see here, a lot of them, if the each initial condition corresponds to a different unique solution to the different differential equation. And that's actually going to be a nice thing to lead off on, that idea, when we talk about section 7.2 and we get into what are called direction fields. And we'll get into that a little bit later. We'll get into that after the break. Are there any questions at all? Okay, let me know. Okay, who's feeling good? Give me a thumbs up if you're feeling good so far with section 7.1, differential equations, or modeling, I should say. That's modeling with differential equations. Javier's good, Ange is good, Jan's good, Taj is good. Excellent, excellent. Okay, let me stop the recording. Let me stop the recording here.